This introduction to work, energy, and power requires that you take notes on the worksheet for Chapter 4. You need to be sure that you have a paper copy of that worksheet available while you do this. And on that sheet, the symbol of the hand holding the pencil is a tip-off that you need to write something on that line. So let's start. What is work? Well, work is simply force times distance moved, that is displacement, in the direction of the force. We'll see the relationship later on between work and energy. As you can see, as written on the sheet there, work occurs when we exert a force on an object and the object moves some distance in the direction of that force. When you do work on an object, you increase the energy of the object. Now, the unit of work in the SI or MKS system is called a joule. And a joule of work is done when 1 Newton of force is exerted over a distance of 1 meter. What follows are examples of positive work, negative work, and no work. Let's go through and label each. And on your paper, just indicate if it's positive work, negative work, or no work. But I will go ahead and add brief explanations. Raising an object to a higher height. Well, that's positive work since you're pushing upward on the object while its displacement is also upward. Gently lowering an object. Well, that's negative work since you're still pushing up on it with your hand while you're gently lowering it. The force and displacement are in opposite directions. Holding an object at a certain height above the ground. Well, that's no work since you are exerting a force, but there's no distance moved. Pushing a cart to the right, causing it to pick up speed as it moves to the right. That's positive work because force and displacement are in the same direction. Pushing on a cart to the left, causing it to slow down as it moves to the right. Well, that's negative work because force and displacement in that case are in the opposite directions. And be sure that you can visualize that situation. Pushing an object sideways, but it does not move. Well, that's no work because, again, there is no displacement. Holding an object at a certain height while moving it from one side of the room to another. Again, that's no work because here the force and the displacement are perpendicular to each other. You are pushing upward while the displacement or motion is horizontal to the floor, so there is no net motion in the direction of the force. Let's go on to energy. What is energy? Interestingly enough, an intuitive definition is not easy to give, even though energy is a much discussed and used physical concept. As it turns out, as written there, you can see energy is the ability to do work. The more energy an object has, the greater is the object's capacity to do work on something else. And the reverse is also true. When you do positive work on an object, you increase the object's energy, since you cause its motion to increase, or at least the potential to have increased motion. And the units of energy are the same as the units of work. They're called joules, that is in the SI unit system or the MKS system. And what I'd like you to do next is to give some examples of types of energy. I'll let you think of a few and write them down. You should have at least 4 in addition to the ones I discuss later on. Later on, after this section, I'm discussing mechanical, kinetic, and potential. I would like for you to think of just 4 types of energy and write them down in addition to those. And you might stop the YouTube for a few minutes while you do this. Okay, well, let's go on to the 2 basic types of mechanical energy. First, there's kinetic energy, and it's symbolized by Ke, or I think our text does E sub K. And then there's potential energy, Pe or E sub P. And kinetic energy is just as its descriptive name is, energy due to an object's motion. And potential energy is energy due to an object's position, because it has potential to increase motion by virtue of where it happens to be. And let me be real tricky here and cut away this box, and you can see what notes you need to put there. Ke equals 1/2 mv squared, where m is mass and v is the magnitude of velocity. So that's something, a mass is moving with some velocity. Its kinetic energy is given by that formula. And in a gravitational field, the potential energy is given of a mass is given by its mass times the acceleration of gravity g times its height. That is, the height it is above some reference point. And now let's go on to the top of the next page where we see this concept of conservation of energy. As it says there are many forms of energy, but in a closed system, we can change from one form of energy to another, but the total energy remains the same. And let me just kind of give a very simple example of lifting a heavy object from the ground and then dropping it. What energy and work relationships occur during this process? And we'll look at 5. Okay, first, while the object is on the floor, it has no mechanical energy. Okay, so that's the main point. It starts with no mechanical energy if it's just lying on the floor. It has no potential energy and it has no kinetic energy. Secondly, while somebody lifts that object and increases its height, that lifting is doing positive work. It's exerting a force and increasing its and giving it a displacement in the direction of the force. And while it's doing that, it's increasing its energy by virtue of the fact that it's increasing its potential energy because it's giving it some height. Number 3, at the top, to the point of where you're going to lift it, its total energy is all potential energy. Potential energy, remember, is mgh, and whatever height you've lifted it to, that's the amount of energy it has. Well, mass times gravity times that height. And this is the amount of work that has been done. That's the total amount of work that was done on the object. Fourth, let's suppose you now drop it. While falling, potential energy decreases because height is decreasing, and kinetic energy increases because it's gaining velocity. The key point is the total energy, the sum of the kinetic and the potential, is always constant at every point while it's falling. It's just that one type of energy is being transferred into the other, but the sum of the two is always constant because the sum of the two gives the total mechanical energy. Then just before hitting the ground, all the energy has now become kinetic. So when you released it, it was all potential. As it was falling, it was potential going into kinetic, and then just before hitting the ground, it's all kinetic. And the total energy of the original mgh has now gone to 1/2 mv squared. Very simple concept, but we'll explore this in a little more detail with more complex systems during our class session. So be sure to review these concepts a couple more times so that you're well prepared for our class on Wednesday. Well, thanks so much for joining me. I enjoyed that.